With this lab, our initial question was, how can we increase the speed of an electromagnetic motor? Our prediction or hypothesis for this was that increasing the number of batteries while keeping the number of magnets the same will increase the current, thus increasing the force on the copper coil. We also thought that increasing the number of magnets while keeping the number of batteries the same would also have the same effect. Our goal was to use tracker technology using our phones as recording devices to record how many revolutions per second the motor was making, and thus we'd be able to compare this to when we were adding more batteries or adding more magnets. For our systems diagrams, we can look here and see the diagram of our setup, our system schema, and the force diagram for the loop, both at the vertical positions and horizontal positions. We also have the right-hand rule, which shows the relationship between the force, magnetic field, and the current. When going into our methods, it helps to look at the systems diagrams to correlate what we were doing with what was actually going on. For our methods, we constructed a motor as shown here in the picture. We then took two 1.5 volt batteries and attached them to the motor using the alligator clips. We would then record the number of rotations made by the motor using our phone's camera. We would then test current by changing the number of batteries to 2, 3, and 4 batteries. And we would also then test the magnetic field by increasing the number of magnets to 7 and 14 while keeping the batteries the same. The most important part of this design was stripping of the wire. One side of the wire needed to be completely stripped while only half of the other. This is because of how the forces cancel each other out. At the top of the loop, the current is going to the right and the force is coming out of the page. On the bottom, the opposite occurs and the force goes into the page. Normally these forces would cancel, but stripping one side will only allow part of the current to go through at that point. When the loop is flipping, if the current was able to completely flow through, it would equal out the bottom and the loop wouldn't move. Stripping the wire on one side and not allowing the current to completely go through allows for the loop to catch up and flip. Ultimately, the circuit is being interrupted.
Assumptions. We assume that all magnets produce the same magnetic field. Adding magnets will increase the magnetic field proportionally. Resistive forces like air resistance and friction are negligible. Adding batteries will also always increase current proportionally. The loop was spinning at maximum speed when we recorded. For results, we tested 2 batteries, 3 batteries, 4 batteries. We saw with 2 batteries we got 8 rotations per second. With 3 batteries we got 11, and for 4 batteries we got 15. This is roughly linear, not exactly, but pretty close, which is what we would expect. Changing the number of magnets, we went from 7 to 14, and with 7 we got 9 rotations per second, and for 14 we got 15, which is again not exactly linear, but close to what we expected.
Based on the results, we found that our data supports the F equals IL cross B equation, as changing both the current and the magnetic field changes the rotation per second of the motor, which is directly related to the force on the motor. However, there were some possible errors with the results, one of them being the stripping of the wires. While one side of the wire could easily be stripped entirely, the other side had to only be 50% stripped, which required accuracy and precision. Stripping too much or too little of the wire could have caused the wire to be exposed when it shouldn't have been, or not exposed when it should have been, both of which would slow down the rotation speed. Another possible error was in the setup, which would only work for roughly 15 seconds before the wire would fall out. This could mean that the wire possibly wouldn't have gotten up to full speed before falling off, thus changing our results. Also, the current wasn't directly measured, just assumed, because voltage was increased and resistance stayed the same. The current could have been different than what we assumed, and could change the data. The final possible error to talk about is the strength of the magnets, as not all of them were necessarily at the exact same strength, which could have affected the results that we got for the magnetic field portion of the result. The motor that we made worked similarly to a DC motor, with some notable differences. Brushed DC motors have a positive and negative field above and below the rotor, similar to the induced positive and negative charge that comes from the magnets in our setup. However, rather than having the momentum carry the rotor past the point where the forces would stop the motor entirely, like in this lab setup, there is a commuter that is able to flip the magnetic field, so that the field is always pushing the motor in the direction that it is spinning.